There are people who haven't done a single one. Well, we're going to start bringing you into the office to have a talk. All right, so two parts. First part today is monotonic functions. Second part is concavity and curve sketching and something called oblique asymptotes, which your book explains in an incoherent manner. I have a much better way to do oblique asymptotes, which should be easy. All right, so let's talk about monotonic functions. All right, I got to give you an example of a monotonic function. So actually, I'm going to give you an English statement here. So English, functions that are monotonic are functions that are everywhere increasing or decreasing are called monotonic. And they can be monotonically increasing or decreasing. So here's an example. Some geometry. If I take x squared and I look at it from 0 onward, this function so x squared over 0 to infinity is monotonically increasing. If I do it again, but reverse it, so this could be something like minus x squared plus 7, then this is monotonically decreasing over 0 to infinity. Okay, so monotonic implies strictness. And so my last question here is going to be this. The constant function, y equals 4, is this monotonically increasing or decreasing? Yes, sir.
Is it neither?
Neither. Okay, so this is neither increasing nor is it decreasing. Okay, so this is really a strict relationship, right? Your function really has to be going up. A function which is flat is said to be non-decreasing and non-increasing, both of those as well. Okay, so let's look at this. So we do have a definition for what it means to be increasing. Let's just recall it. So the definition was if you pick 2 points here, x0 and x1, and x0 is less than x1, then if this function is increasing, we should find that, so if x0 is less than x1, we should find that f of x0 is less than f of x1, right? So that's the definition we had for increasing, but what else do you notice about this function? What does the tangent look like at this point? Something like this, right? What's the tangent at this point? Something like this, right? What's the tangent here? Something like this. What's true about all those tangents?
They get steeper.
They are getting steeper, they are increasing, but what's one property that sort of all of the lines have in this case?
Positive.
They're positive, right? At each of these points, the tangent line has positive slope. At any of the points in here, the tangent line will have negative slope, right? So this is actually going to be true generally, right? That a function is monotonically increasing when its derivative is increasing, or when its derivative is positive, and it will be monotonically decreasing when its derivative is negative. Right, so that's what derivatives tell us. It tells us about how functions are behaving. If they're, and one of the ways that they can behave is they can be increasing or decreasing. Okay, so now we need the algebraic definition for this. And we can actually prove it. So I'm going to use this new word, but don't get too stressed about it. It's a corollary. And I had a German professor who had this terrible joke. He says, it's a corollary, it's not a car. You know, there's a Corolla, but anyway, I told you it was a terrible joke. A corollary is just like an immediate consequence of something else. So this is a corollary of the mean value theorem. It's hardly worth being given a name because it's so immediate. But, well, in any case, so provided, so here's the toll you have to pay. F is continuous on this open interval f is differentiable on the closed interval.
Is
Yes.
open or closed? Because you did the opposite.
F is continuous on the, closed interval. F is differentiable on the open interval. So I wrote it correctly, I said it wrong. Okay, so provided this is the case, then we have F is said to be increasing on AB when, and then all I need to say is this function is increasing when all of its derivatives are positive in this interval. So we say it like this, right? For every point in the interval, the function has to have positive slope. Strictly positive slope. Right again. For every x in the interval, f prime of x has to be positive. Hello, Suki.
Morning.
Morning. Okay. The f is decreasing on AB. I bet you can get it. This is when for every x in AB, we have that the derivative is less than 0. Oh boy. Right, so basically this corollary means that in order to test if a function is increasing or decreasing, all you have to do is investigate the derivative. Now, I have a proof of this in here. I'm going to skip it. If you're interested, you could take a look in the notes. It's actually not very hard to prove this. But I guess we're a little bit more interested in examples. So here's an example. When is the function x cubed minus 12x minus 5 increasing, and where is it decreasing? Okay, give that a try. While I wipe down the board. Okay. So this is a function, it's a parabola, right? So if we just keep in mind that we're going to have something like this, we should find that it's decreasing here and increasing here. So I sort of already know the answer before beginning. Let's just give this a name. Let's call it f. So I can say f of prime, or f prime, is 3x squared minus 12. We need to know when this is positive and when this is negative, right? Oh, sorry, geez. This is a cubic. All right, so actually the function f looks like this. So we should discover that it's everywhere increasing. So can we get that from here? No, what is going on here? Did I write the right thing? Okay, well in any case, the derivative of this is, or the factorization of this is 3, let me see, x minus 4, x squared minus 4, which is 3x minus 2, x plus 4. So what is this telling us? This is telling us that we should be, well, we got to look at the number line here. Right, so the derivative looks like this. It's some parabola, and it's going through, not 4, 2. All right, it's going through minus 2, 2. So I know that this function is positive. So f prime is positive if you're less than negative 2. If you're in between negative 2 and 2, you're negative. And if you're beyond 2, you're positive, right? So maybe some of you did these charts in high school. But I'm basically just trying to determine what f prime is over these intervals. Right? Because we just determined that if f prime is positive, that means the function has to be increasing. If it's negative, that means the function has to be decreasing. And positive derivative means that we're increasing. So I can really specify that f is increasing on these intervals. Whoops. Minus infinity to minus 2, and then 2 to infinity, and then f is decreasing on minus 2 to 2. We should plot this. I don't really have it. How can the cubic be decreasing? I guess we could have something like this. Right, so our cubic should look something like this, right? We increase, and then we're decreasing for a bit, and then increasing. But that's the point of making these investigations, because soon we're going to want to try to draw these pictures without drawing, or without using a computer to draw the graph. Right? This is all just trying to strengthen your algebraic geometric correspondence. Okay, I'm going to draw a big picture, and we're going to label it. Should be easy. This is something called the first derivative test that we're going to talk about. Okay, so let's go and let's label the following graph. All right. We're going to go like this, and then up like this, and then down all the way, and then up like this, and then maybe like this. Okay, so I'm going to give you some points. And here, and here, and here, and here. Okay, so let's try to go about labeling this. So we have some clear divisions, like this. So this is supposed to be a this is supposed to be a cusp here. Something weird. Okay, and then here's the end. Okay, so here's a function f. Is the function increasing or decreasing on this interval from here to here? Increasing, going up. Okay, so what does this tell us the derivative should be in this area? Positive. Derivatives here should be positive. Is that true? Well, it seems to be the case that these will always be upward pointing derivatives. What happens here? Well, the derivative is flat, right? So this has to be a critical point. But nothing else really is interesting, right? It's just a point where the derivative is flat. We'll soon find that these points actually correspond to points of inflection. That's the next lecture. Okay, what about up here? We have flat derivative. Well, not at that point. You need 2 points before you can be increasing or decreasing. So I'm really talking about single point. So that single point is a critical point. Right, and the derivative is flat. The derivative is flat. And also we can see that if we move out a little bit, it's negative and positive. If we move left, yeah, you go down, you move right, you go down. Right? So this actually is a local maxima. It is not the global maxima because this one's kind of high. Okay, so between here to here, we're also increasing, and it's still the case that the derivatives are positive. From here on, right, so the derivatives are positive, 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 decreasing, decreasing until it hits 0. And now it's going to be negative here. So the derivative here is negative, which means that we should be decreasing. That's what we find. We hit another flat critical point. This is where f prime is equal to 0. This is a critical point. And this is the local minima. And it's also an absolute minima. All right, we keep going. We're increasing here, which means that the derivative should be positive, which we can see that it is. There is no tangent line here. Derivative does not exist, but that means that this is a critical point. And also it's the absolute maximum as well as a local maximum. Okay, so then we're decreasing in here. That's because the derivatives are less than 0, right? You can see that the slopes are negative. And the slopes continue to be negative, so we're also decreasing in here, f prime, and then here's another critical point. Okay, so critical points don't necessarily correspond to absolute minima or maxima. Yes, sir?
Doesn't the derivative have to exist for a critical point to be there?
Did we define it to be the... No. We defined a critical point to be where the derivative is 0 or where the derivative doesn't exist. right? That's why we have to come up with the name critical point. I'd rather say, look, where the derivative is 0, but it's actually where the derivative is 0 and where the derivative does not exist. So we've compactified that into a term called critical point. Okay, so that wasn't too bad. So let's sort of codify the observations we've made here. Namely that it seems to be the case wherever we find localized minima or maxima that we see that the derivative is flat. So here's our observation. Okay, local extrema occur here at places that look like this. So I'm just going to call this critical point C, or look like this, or look like this, or look like this. All right, so all localized maxima have to sort of be one of these type of conditions. But we don't, but there is no local maxima, minima, at stuff like this. All right? So if we just call this all C. Now, notice that in all cases here, the derivative is 0. The derivative at C is 0 here. The derivative of 0, the derivative is also 0 on these ones, right? We have flat tangents here. We have flat tangents here. But it's only these ones we're interested in terms of isolating local extrema. Right? So we're going to have to sort of figure out when it's the case that we have this versus this. And we do that with the first derivative test. First derivative test. Provided C is a critical point in this interval, F is continuous over this interval, I guess the closed interval, and then F is diffable or differentiable on the open interval. And this is maybe confusing. The open interval, but maybe not C. Right. Yes, sir?
The middle one open or closed?
Yeah. Clopin. There is actually something called clopin. Yeah, closed open sets, yeah. Okay, so provided C is a critical point, F is continuous, and F is differentiable, we just have to codify the cases, right? So here's a case. Okay, so we want to basically come up with a rule for finding this, right? We want to be able to pick up this and eliminate this. Okay, so we're going to have two cases here. The first case, case 1, is going to be this case. Case 2 is going to be this one, and case 3 is going to be the other one. So think about it. What algebraic conditions do we need in order to conclude we're in this case or this case? Think about it. I'll wipe down the board and give you the answer. How can you codify it? Right, that's the thing we're looking for on the graph. But suppose you couldn't see the graph. Suppose all you could take was measurements. How could you figure out that you're in that case? Okay, let's look at this more carefully. What I'm going to do is going to draw a number line under here. So here's the x, which is the real line. This is the critical point at C. We've already determined that f prime at C is 0, right? So we're flat here. What has to be the case about the tangent on the right-hand side of C and the tangent on the left-hand side of C? Yes, sir?
On the right-hand side, f prime would be positive, or
All right.
greater than 0.
Yes?
And on the other side, it would be
Sure.
less than 0.
So I'm going to say it like this. I'm going to say if we take C, if we let, and this is, I don't know why, we shouldn't be too scared of this. I'm just going to say let epsilon be greater than 0. All this means is like, I just need a tiny positive number, right? That's all I want, a tiny positive number. So that means that C plus epsilon is out here, and C minus epsilon is down there. That's how I'm going to get a number to the right of C and to the left of C that's not too far away. Okay, so I'm just going to write what you said. If we know that f prime of C is 0, and we know that f prime of C plus epsilon is negative, and we know that f prime C plus epsilon, whoops, not C plus, C minus, is positive, then we can conclude this is the case that we're in. Yes, this case. I'll rewrite it, right? You look skeptical. Yeah.
Oh, I get it.
Oh, you get it, okay.
I just looked like that.
Should that be positive?
Did I screw up a sign? Which one should be positive?
Just switch them around.
Yeah.
C plus
What
epsilon.
line is there?
No, oh yes, you're right, you're right. Okay,
Yeah.
these should be switched. Even gods make mistakes. Okay. Human race, for example. We're not a mistake. I like the human race. That's for YouTube, right? Demonetized. Oh, I swear all the time in class anyway. Demonetized. Whoever posted the change my mind meme on the last lecture. Okay, let's get the other case then. I'll just write it out more full-fledged, right? So we're trying to find, did I just do this one? Wrong one. Let's do the other one. So now we're trying to find localized minimum. So how do we find this localized minimum? Well, I'm just going to put it again on the number line. We'll say this is C plus epsilon, this is C minus epsilon. So if we know that f prime of C is 0, and we know that f prime of C plus epsilon is
Greater than 0.
positive, you're correct.
Yeah.
And f prime C minus epsilon is negative, then CF of C is a local minimum. Right, so now I've given you yes, miss.
Isn't this the case that we just did?
I liked it so much that I did it twice.
Yeah.
You do the other one then. God damn it.
Maximum.
I'll do it. Fine. It's fine. It's fine. Just gonna do this. I gotta do that. That means I just gotta do one of these and give her one of this. Is that right? We have to be positive here. Yes. We have to be negative here. Thank you.
Wait, don't you have to start all over?
Yeah, it's
Because
maximum.
you screwed up. Yeah. Because that's what you made us do it 3 times yesterday. He doesn't follow. I know.
Stop throwing my advice back in my face. Right? You are to take my advice. I get to not take it. Right? I don't need my advice. You take it. Okay, so this is the first derivative test, basically. You can look at a critical point, and if you move a little bit right and move a little bit left and investigate the nature of the derivative, you can determine if you're at an absolute minimum or absolute maximum. If it doesn't fall into one of these two cases, if you find some other weird behavior like a point of inflection, nothing is conclusive. Right? So I'm not saying that these are the only cases. I'm saying if you discover a situation like this, then you can conclude. Right? Don't over conclude here. All right, example. Find all local extrema of this function. F of x is equal to x to the power of 1/3, x minus 4. Go crazy. I'm going to do a couple laps. So find me all localized extrema of this. Yeah, all absolute mins and maxes. Memes are my favorite. My computer science kids. Oh. We have to like dedicate a part of Piazza for like meme posting, just so it doesn't contaminate the rest. What should I do during these breaks? Math memes.
Yes.
Okay, hit me. Wait, you literally brought me
I literally saved them on my phone.
physical meme. Oh, it's on your phone. I thought she printed them out to show it to me. Look. Repost this. Oh, okay.
What did I do? -1 can equal x squared. Wait a second.
It can if x is I.
We're not doing imaginary numbers, right?
Complex numbers.
Complex numbers? I call them imaginary. Do you really?
I really would. Do you
You
want
have
to
a
see
gallery.
Meantime,
You sent it into
the WhatsApp.
you sent this morning.
Oh yeah,
Oh, this is a funny one. It's a roast. Yeah, okay. Yeah, okay. Wait.
How's that a math meme?
Wait, so that one.
Okay, first of all, I don't think any of you are dumb. I've said this many times. Dumbness, I would forget. Laziness is unforgivable. Physics, mathematics.
Oh, never mind.
It's already applied mathematics. I hate applying mathematics.
I love it.
Like applying it at all.
Fuck it. Okay, I'm gonna give you the answer. All right, so we got this. What I'm gonna do is I'm gonna be a little bit tricky. I'm gonna factor out. I'm just gonna factor. I'm gonna expand this. So this is x to the 4/3 minus 4x to the 3rd, just so I can avoid a product rule. This means that f prime of x is 4/3 x to the 3rd minus 4/3 x to the minus 2/3, which is equal to, now this is going to be tricky, right? I'm going to factor out this, right? I'm going to factor out this, so I'm telling you that's happening. Right, so I'm going to factor out x to the minus 2/3, and I'm going to get in here x minus 1. Right, so just be aware that that's where that came from. This means that I have f prime of x is equal to 0 for x is 1, and f prime of x is undefined for x equals 0. So that means we just have to investigate how f prime looks on some intervals. So here's 0, here's 1. Let's also look at it at -1. So I have to pick, I need to know if f prime is positive or negative in these intervals. Right? That's so we can use this. Right? This is going to be my like c minus epsilon, c plus epsilon will be in here. So the endpoints you have to draw. So that's an endpoint, this is an endpoint. I drew this one because I'm going to choose to evaluate f prime at -1. I'll also do it at 1/2. And I'm also going to have to do it over here at like 3/2 or something, right? So the interval is here. Then you have to pick one point in each of your intervals. There should be one more point than the number of intervals. Right? We have an interval. Maybe I'll redraw this and explain it. Okay, here's the real line. I need to figure out if f prime is positive or negative over the real line. We know that this is f prime here. And we know that it goes through the axis at 0, or it's undefined at 0, and it's 0 at 1. So these are the intervals that I have to investigate, which means I need to choose a sample point somewhere here, and somewhere here. So the one that I can pick here, let's call it 1/2. The one here, let's call it -1. And over here, let's call it 2. Okay, so what's f prime at -1? Okay, so look at this. This is just going to square something. So no negative can come from this term. Right? Because you take a negative, you square, like that negative really puts it to the bottom, right? So there's no negatives will come from here for any number. That means the sign of this term is totally controlled by this one. So where is x minus 1 positive?
When x is over 1.
When x is bigger than 1, right? So we should be positive here. If I put 1/2 into this, it's going to be negative. And if I put something really small, like a negative 1,000,000, it's going to be negative. Okay, so what have we found? There's no change from here to here, but there is a negative to positive change at 1. So that means we found, all right, so let me label this. So the function, like f then, is decreasing, decreasing, and then increasing. And the only way for a function to decrease and then increase and to be continuous is for the function to do this. The function is doing something like this at 1. Right? Decreasing and then increasing. So we found a local minimum at 1. What's the evaluation point? Minus 3. Minus 3. Okay, 1 minus 3. Okay, so at 1 minus 3 on that function, which we didn't draw, we know that there's a localized minimum. Yes?
So even if we had to change like before and after 0, it wouldn't matter because the point at 0 does not exist. I mean, it's
No, if there is a change here, yeah, then we'd have to invest. There could actually be localized minimum there.
even though at 0 it's undefined.
Yeah, we have lots of places where we can get undefined behavior in the, like here is there's no derivative, but there's still localized maxima,
Oh.
right? So that's why. We can always like do weird things and connect functions with lines
So
rather.
what would we do? Do we plug in 0 on that original function and see if we get a number?
Well, I'm saying like this was a polynomial to be, well, not really. You just have to investigate a bit more. You'd have to see if there's an asymptote there and like take that, like, I'm not saying that there's really, we're gonna have to take all the information that we've learned,
Okay.
right, and then connect them together and see what type of function can satisfy all those conditions simultaneously, which is what we're gonna be doing next. Okay, so that's that. I'm just gonna wipe down the boards. So if you wanna chat for 5 minutes, go crazy, but this is not a break. It's a chat break. Okay, we'll do 3 more pages, then I'll give you a proper break. So let's just talk about concavity and curve sketching. Well, first we'll do concavity. So when your function has a concavity, you bring it to the dentist, right? I'm hilarious. All right. Is concavity something that you were taught in high school? A little bit? You figure out what it is, though. That's fine. It's weird because you definitely need derivatives in order to talk about concavity. But in any case, maybe some of you will be able to identify this as being a concave up shape. And perhaps some of you will even be able to identify that this is a concave down shape. This one. Well, what is the defining property here for concave down and concave up? Right? This is the geometry. What's the algebraic codification of these conditions?
It would be the same thing we did for the actual function, but we would do it to the derivative. So you know how we derive the first one and we can see how it goes from positive to negative and negative to positive?
Okay, so you're saying that we should investigate the tangent lines.
Yes.
Okay, so let's investigate the tangent lines. So I'm going to start drawing tangents on this one. So we have something steep negative, less steep negative, very less steep, 0, positive, shallow, positive steeper, positive steeper. So what is happening to these tangent lines as we move? Yes, sir.
They're increasing.
They're increasing, right? This is a really big, it's a big negative number. This is a less big negative, like this is a really steep negative slope. This is a less steep negative slope. Less steep negative slope. So this is really like -3, -2, -0.5, 0. Positive 0.5, 1, 2, right? So as you see, the slopes of these tangents are increasing as we move forward. That is the property that defines concavity. Another way of talking about concavity, I don't really like this word. If the first derivative is measuring how fast you're increasing, the second derivative is measuring curvature. Right, so that's actually what second derivative testing is telling us. It's telling us a little bit about the curvature of these things. And the reason that's interesting is because if we know that this is a localized maximum, or if we know that this is a critical point, and we know the curvature, then we can conclude that it's a localized maximum or minimum. We'll get there. Okay, so anyways, to be concave up, if this is a function f, we know that the derivative always has to be positive here. Let's play the same game here. What's happening? This is really steep positive, less steep positive, 0. Not very steep negative, very steep negative, right? So in this case, we have the derivatives. What am I doing? That is true, but not enough. F prime is increasing. And F prime is decreasing. Okay, but if F prime is increasing, what did we just learn that this has to satisfy? We just had a whole lecture on increasing, decreasing.
The derivative has to be positive?
Yeah, the derivative of this has to be positive, right? So if F prime is increasing, this means that F double prime has to be positive. In this case, this means that F double prime has to be negative, right? If we look at the derivative of the derivative has to be positive. That's how we can measure if the derivatives themselves are increasing. All right, so here's a couple definitions for concave up. So let I be an interval AB. Then F is called concave up, which we just say CU next Tuesday. Then F is called concave up when for every x in the interval, we have that F double prime of x is positive, which is equivalent to the statement F prime is an increasing function. Okay? To get concave down, it's just the converse of this. I trust that you can sort of extract it. It's in the notes. All right, so now we can talk about something called the second derivative test. And this is basically like a time-saving technique, right? Because if we're looking for localized minima and maxima, so here's a localized maxima. If we know that this is a critical point, we could always check some values to the left and to the right, but we could also just check the curvature. If we know that this is critical, so like if F prime, if this is C down here, F prime of C would be 0, and then F double prime at C would be, have to be downward, so it's negative, right? So if you have 0 slope and then downward curvature, you can conclude that you're an absolute maximum, right? So this is just basically tools for isolating absolute maximums and minimums. So let's give that a try. So I have to write the rule. Okay, so for an interval on the real line, if f double prime is greater than 0, right? So if f prime is an increasing function on I, then f is concave up on I. And if f double prime is less than 0 on I, this means f is concave down on I. All right, so here's an example. If we look at the cubic, okay, so this is y equals x cubed. This means y prime is 3x squared. This means y double prime is 6x. So note this says that there's a critical point at 0, 0. Here there should be, we have y double prime is equal to 0 at 0. So that's going to be what we call a point of inflection. But what can we find here? So here we have downward curvature. So here's curvature downward. And here we have curvature upward. So we should find that, well, what is true in this space? So if the second derivative is 6x, that means the derivative is positive in positive x and negative in negative x. So is this the case that this is concave down? Sure it is. Is this the case that this is concave up? It is, right? So what I stated algebraically actually seems to make sense geometrically. We just have to sort of investigate what this is. Why is this special? And it's special because, first of all, the second derivative is 0 there. But we can also see that there's a change in curvature, right? Curvature is downward, curvature is upwards. So a curvature change will always happen when the second derivative is 0 or undefined. It's kind of like a critical point. And this actually we're going to be calling a point of inflection. Okay, so a point of inflection point C, f of C is called a point of inflection when the derivative exists and f changes inflection. Okay? So point of inflection is this situation where you just have to specify that the derivative there actually exists. So here's an example. I don't know why I called that the second derivative test. Anyways, this is the second derivative test. I think this is just a test for concavity. Here's a function. This is y equals x to the 5/3. There's clearly a point of inflection here, right? The concavity is changing. So let's just confirm that the algebra works out the way we need it. This means that y prime is equal to 5/3 x to the 2/3. This means that y double prime is equal to 10/9 x to the minus 1/3. All right, so this sort of gets a little bit messy at 0, but we really only care about its sign. So what is 1 over? All right. So this is the third root of x. So the third root of something positive is positive, and the third root of something negative is negative. Right, so the second derivative is telling us that we should have upward concavity when x is greater than 0 and negative concavity when we're less than 0. That does actually seem to be the case. Right, so here f double prime is less than 0, f double prime is greater than 0. It's actually undefined at that point, but that's okay. not my favorite discipline. Like this subject area, we have plotting tools now. It's not really the 1800s anymore when this is the only way to get information out of graphs. But it's still good to know that the algebra that you're doing has really strict geometric correspondence. Okay, so don't call that other thing the second derivative test. I think I'm just losing my mind today. That's what happens when you write lectures during a Raptors game. Okay, so this is the second derivative test. And it's basically just a test for figuring out if we're in this scenario or this scenario. All right, so I'm just going to write a bunch of stuff. So provided, what do we need? The second derivative is continuous on the open interval. And we have some point C in it. Then we have three conditions, right? Then, condition 1. I think that's this one that we're going to talk about. All right, so basically I'm going to say if we're in this condition, we can conclude that we have an absolute, we can conclude that there's a localized maximum here. So what do we need? I need a flat tangent, and I need downward concavity. So this means I need f prime at c to be 0, and the concavity to be downward, which is a condition on the second derivative, which I'll write. Okay, so we need f prime at c to be flat. Well, f prime at c has to be 0. That's a flat tangent. And we need f double prime at c to be negative, right? That's telling us that the curvature at that point is downward. Right, so flat tangent, downward pointing, you must be CFC is local maximum. Right, so now this saves you from having to play this game where you move a little bit right and left to determine what the signage of the derivatives are. Right, so if you can get a flat tangent in curvature, right, the curvature is telling you, like, if you're flat tangent, if you know you're in this situation, and that's your point, you either have upward curvature, which tells you have a localized minimum, or downward curvature, which tells you have localized maximum. Right, so that's the first one. So the second one is this case, the localized minimum. So this means you need a flat tangent, and you need the curvature to be upward. Whoops, C. This means that C, f of C, is local minimum. Okay? If you have the case that f prime of c is 0 and f double prime of c is 0, you get no information. This doesn't mean that there isn't localized minimum or maxima there. It means that this test is inconclusive in determining that. That's different. This is not, right? Otherwise, this would really be a test. Okay, why don't you guys take a 10-minute break, and then we'll discuss slant asymptotes and curve sketching. 10 minutes, for real though. Real 10 minutes.